We're recording, so conversing and you're in the middle of something really important, I'll pause it for a minute. Okay, no, people did fairly well with this one. This might not have been a fair question, a completely fair question at this point, because I think it's the next section in the chapter that tells you how to find the equation of that one. Okay. And I'm thinking you have the information to do this. Let's just see what you can do. One thing you can do is you can find the slope in each case, right? And you do know that the equation of a line is y equals mx plus b, right? Okay. I think that's in the first section, isn't it? Look a little blank. Okay. Maybe I should look a little closer. And look at the problems. We're asking. Okay. Anyhow, so we get the slopes there. So we can sketch the line, although it's not going to be very accurate. The line has the equation y equals mx plus b, where m is the slope and b is the y-intercept. Now it looks like the y-intercept is about 1 here. If this is 3, that may be 1. Okay, but 11.9 really isn't plotted particularly well. So, so whether you're seeing this or not, you're seeing it now. Okay. The b is the y-intercept, and it's maybe 1, because it looks like that one maybe. So if you have a graph and you know what goes through the y-axis, you got your b. If you have the information to find the slope, then you can just write down the equation. Okay. Well, slope here as we've draw a vertical arrow and a horizontal arrow, you get the slope. We've done that for rates of change. We've done slopes with the toolkit functions. So this should be very familiar to you. So the rise goes from 5 to 9, it's 4. There's a formula for it. You just calculate it. The run is 8, so the slope ½ So now we can fill in slope. So for the first y-intercept is maybe 1. Now what I've written there is the slope the equation might be y equals 1/2 x plus 1, but probably not quite. It's probably somewhat close, but I don't have confidence the y-intercept is exactly 1. There's no reason to suppose that it would be. It just looks like it might be. And the graph isn't drawn very accurately. So I think the y-intercept is going to come out different. Let's test this. Got the 0.35, so if x is 3, y should be 5. Now I'm going to write y equals with the question mark over the equal sign. We're asking a question whether y equals 1/2 of 3 plus 1. Okay. Well, that's 2.5, not 3, not 5. Well, yeah, that's 1/2 of 3. Yes, 1/2 of 3 plus 1. Well, that's not 5. So our function is somewhat off. If we plug in x equals 11, we get like 6.5. Okay, so our equation isn't. I'll say the equation isn't very good. And well, we know that y is 1/2 x plus b, don't we? And we know that when x equals 3, y equals 5. Well, that means we can replace y by 5 and x by 3 and figure out what b is. Get 5 equals 1/2 of 3 plus b, and we can solve for b. I'm not going to do the solution. You can do the solution. I'd multiply 3 by 2 to get rid of the fraction, but you could do 1/2 of 3, which is 3/2. Subtract that from 5, okay? And you get 3.5, okay, which is 7/2. And that's 3.5. Y equals 1/2 x plus 7/2. Then if we go back and plug in x equals 11, we get 11/2 plus 7/2. 11 and 7 is 18. That's 18/2, which is 9. And we get the coordinates 11. Okay. If x equals 11, we do get 9. So the equation works for this point and it works for that point. Okay. We haven't really verified that it works for this point, but we use this point to get the equation. And then it correctly gave us this point. So we're pretty sure it's right. If we want to be 100% sure, we go ahead and plug in 3. If x is 3, you get 3/2 and 7/2. It's 10/2, which is 5, which is what we ought to have. Okay, so it's a very simple process. If you have 2 points, you could get the slope. Okay, and just do what I have. So once you have the slope, the only thing you don't know is b. Since you know x and y for either one of the points, you plug in the x and the y. All you need is b. You solve for b, and then you write the equation, and it works. All right, that's not a particularly difficult procedure, but you're probably taught to do it using a formula. Okay, something like y equals y2 minus y1 over x2 minus x1 times x. Okay, and then plus something else complicated. Or a simple formula equation would be like y minus y1 equals y2 minus y1 over x2 minus x1 times x minus x1. Okay. That's a good equation. Use it if you need to. Also, really want to see you do this because, again, it helps you much better understand what's going on with the graph. Following a formula doesn't necessarily do that. Okay. Well, we get the equation of this line. It's pretty easy. Five units here, 10 units here. Rise 10 over 5. Slope is 10 over 5 equals 2. What's the y-intercept? Can you show me with your fingers? Yeah. See a lot of people with both hands. I can't hold up all my fingers. I'll drop the chalk. But the y-intercept is a coordinate where you pass the y coordinate where you go through the y-axis. Okay. Yeah, right there is your y-intercept. You can read that right off. That's interesting. Okay. Okay, now what about this with the population? Well, it did a nice job. Almost everybody had a good population function written down. $50,000 plus 500 T. Because every year you add 500. If T is 1 year, then you will have added 500 and you'll have 50,500. If T is 10 years, 500 T would be 5,000. So you would have added 5,000. At 500 per year, of course, that's what you do add. So you get 55,000. Now, with 50,000, 57,300. Well, P's a population, it's 57,300. Okay. And P equals 50,000 plus 500 T. Well, P is this and P is this, then 57,300 equals 50,000. 50,000 plus 500 T. All for T. Well, we subtract 50,000 from both sides. And you get 500 T equals 7,300. 7,300 or 500 equals 14.6. Now, a lot of people got 14.6 just using common sense. You're going to increase the population by 7,300 at 500 per year. So you divide 7,300 by 500 And there you have it. Well, that bypasses the whole concept of using the equation to solve it, because most of the time it's not going to be obvious, as obvious as it is in this case. What you have to do for most equations, you got to carefully write the equation, and then write the function, write the equation, and solve the equation carefully. Then make sure the answer makes sense. The entire process. Okay. Well, that makes sense. Okay, we have a situation where the rate of growth is R of t, which is 2 plus 3 times quantity t minus 60, where t is the temperature. Okay. Now, if t is a function of time, and I'm not going to specify time in hours, time in days, whatever. What's the rate R at time t? If I tell you what time it is, can you find R? Okay, to make the question a little simpler, can we figure out if you're given the t equals little t, time is 3, can you figure out what the rate is? Okay, y'all are doing pretty well with this. I dropped a couple of hints, but not much. Okay. Now, what I did say is some people try to plug 3 into this. Okay, but this is little t. There's no little t in here to plug it in. Now, as soon as I say that, people are going to see, oh yeah, there's a little t here. So that's the only place I can use the little t. So if I plug little t in here, I'm going to get big T. Okay. Now, one thing you want to be careful of, because some people are reading this as big T multiplied by T. No, this is big T as a function of T. Okay. You don't divide both sides of this by T and get big T. Okay. Big T is whatever you get when you substitute little t. Okay. So big T of 3 equals 90 minus 3 squared, which is 84. That is your temperature. Okay. This is your temperature times little t equals 3. And at least a few people were wanting to divide both sides here by 3 then. Okay. You can't divide t of 3 by 3. T of 3 means t evaluated, the function t evaluated in time. Okay, so we plug t equals 81 into R of t. R of 81 equals 2 plus 3 times 81 minus 60. And that's going to give you 21. 3 times that is 63. 61, you're going to get 63. Everybody gets 63. Or did I do my arithmetic wrong? Everybody get 63? Yeah. Okay. Check my arithmetic. I do it all in my head and you never know what's going to happen there. Okay. Makes sense? Now, what's the rate R at time t? Okay. How are you going to figure out R at any time? The formula for R at time t. What we just did was we found big T at a given value of little t. Plug this into our big T function, right? Excuse me. Yep. Yeah, somebody pointed out I did a bulleted calculation here, although you didn't use that word, you used much worse one. Yeah, when I multiplied 3 by 81, I got 63. But then when I added 2, I reverted back to a 1 on the end instead of a 3. And I added 61 instead of 63. Okay, I warned you. Okay, watch me. I do these things in my head. Sometimes things go haywire. Sometimes it works out pretty well, and sometimes never. Okay, so anyhow, what we did was we found big T at a given value of little t, then we plugged it in here, right? Okay. Well, we can do that. Given T, we calculate big T as 90 minus T squared. Given big T, R equals 2 plus 3 times 18 minus 60. Okay. Well, if we're given little t, we can find big T. There's our big T. So if we plug that in here, we got a formula for R in terms of little t. We plug 90 minus T squared for T in our R of T function. We get R of big T is R of 90 minus T squared, right? Well, what's R of 90 minus T squared? R of big T is this. R of 90 minus T squared, we replace big T by 90 minus T squared. So we better replace this big T, what we did with composite functions, and that's exactly what's going on here. And we feed one function into the other. So if we use the formula for R of big T, and this is something I hope you're familiar with because we've done quite a bit of it by now. 90 minus T squared replaces big T, so it replaces big T here too. And we get 2 plus 3 times 90 minus little t squared minus 60. Okay. Well, to be a little more explicit about what we've done, we write this as R of big T of little t. I'll write it. R of big T of little t now is a function of little t. Okay. And now you know how to calculate R directly if I just give you T. So if T equals 3, well, you're going to get the same thing you got before. T equals 3, T squared is 9. 90 minus T squared is 81. So we're right back to where we were here. Okay. Now, if you want to calculate it for T equals 5, okay, you get a much lower growth rate. Let's get 2, 4. Okay, so there's an example of a composite function. And you have a name for this. You call this R circle T, big T, which is a function of little t. Okay. Now, 90 minus 60 is 30, right? And you can do a little simple algebra. You can simplify this. You do 90 minus 60, you get 30. Multiply through by the 3, get 90 minus 3t squared. 90 and 2 is 92, and there again. Okay. That's all stuff I don't hope you would do. Yeah, just routine simplification. Okay. Well, the whole idea of a composite function is you plug one function into the other. That's how you form a composite. And this is an example of an application of composite functions. You'll see a small handful of good examples in the homework on composite functions. Fairly long assignment, which is why I wanted to put it off till tomorrow. It'd be reasonable to ask you to do it tonight, but it's always good to talk about it and give you an extra day to get it done. Okay. So, modified design schedule slide. Okay. Okay, what's going on? I'm doing the graph of actually another toolkit function, probably the easiest one. Okay, this is all you need. You don't even, you're going to draw your x-axis and your y-axis, your dots in the middle, and you just go from the lower left-hand corner to the upper right-hand corner. So I ask people, what's the x coordinate of this point and what's the y coordinate? So a few people answered. Does everybody know? Some of you know, I know. You had it. Now you had it. Okay. Here's the origin, right? How far do you have to go over here? 2. How far do you have to go up? 2. It's not 4 because the origin's here in the middle of the square. Okay. Is that clear? When you go half the square over and half the square up. Okay. It's a 4 by 4 square, so you go 2 over and 2 up. So this point is 2, 2. This point, well, both. You got to go in the negative direction. 2, negative, 2, negative, right? You got negative 2, negative 2. How are x and y related? Can you give me a symbol with your fingers? It tells me how x and y are related here. Yeah. So they're equal. Okay. They're always equal. You can do that geometrically. Okay. I mean, they're equal here. They're equal here, right? So I'm just going to say they're equal. I don't want to go through the geometric argument for time considerations. Okay. So this is the function y equals x. And we call it the toolkit linear function because it's a straight line. Line, linear, okay? That makes sense? Very simple function, straight line. Okay. Now, if I vertically stretch this graph, where it's now 8x4, construction is still the same. Your dot's in the middle, and you just connect the upper right hand to the lower left hand corner. Okay. Now, what transformation did we just do? How much vertical stretch was there? Okay, if we construct the thing in an 8x4 rectangle, same rule, upper right hand to lower left hand with the red dot in the middle. So here's our X and Y axes. Now what are the coordinates at this point? Show me with your fingers. What's the X coordinate? What's the Y coordinate? What's the X coordinate? 2 and 4, right? It's obvious, you got to go over 2 and over 4. And I didn't draw that very symmetrically. Still get the idea, okay? Well, what's the function then? If you vertically stretch a function by factor 2, well, statements. General rule, if you vertically stretch any function by factor A, you get y equals a times f of x. It becomes a times as much. Now, if a is less than 1, they call that a compression. It's still a times as much. If it's 1/2, then it's 1/2 as much, and that compresses it. Like your 4x4 rectangle become a 2x2 rectangle. Okay. Here we stretch by what factor? We stretch by factor 2. Okay. And I want to work the f(x). This I'm going to use y equals f of x equals x. That's just this function, but I'm calling it f of x now so I can apply this rule. Okay. We get then y equals 2 f of x, which of course is 2x. F of x is x, 2 f of x would be 2x. You want to understand that because we're going to be vertically stretching a lot of functions. And we're going to get into doing it with quadratic functions sometime along next week, okay? Then it becomes a little more complicated, but you're pretty familiar with quadratic functions. You've had your x squared graph, we stretched it, we've moved it around, and you know how to get the equations, I hope. Of course, you can't take the test, I certainly hope you do, and I hope you did when you took the test. Okay, if it came up. So there we have pretty much a lot of what we've learned about stretching and moving functions around. What if we now take this function and move it to Yeah, I'll move it over this way. Okay, so now I'm gonna take this function, and this is my 8x4 rectangle. And there it is. And of course, you know, I've told you how we extend the graph of your basic exponential function outside that 4x4 square. Or your squaring function. You might or might not remember. I didn't test you over it, so you probably didn't think that hard on it, but we'll talk about it again later. It's easy to understand how to extend this when you just keep a straight line going. Don't let it curve, right? There's your straight line. Now, what do you think the coordinates of the red dot are? What do you think the y coordinate of the red dot